It's really odd. I don't understand.
Okay.
Well,
Take a look at
the
that
critical
again.
thing is particularly X3 is numerically large. It's 25. Multiply 25 by 8/3 for whatever it is, whatever parameter that is.
Beta. You get
Beta,
66.
yeah. You get 66, which overflows by 3. And so it becomes.
No, yeah, I understand.
3.
I understand that, but so you should be able to solve that by like just putting as an input to the multiplier a shifted value of either eta or 25. You can just shift that as the input, and then the output should be fine because you've already shifted the input. But
That's
they were
correct.
doing that and not having it, and they're still having the overflow problem.
That,
Yeah.
so then check the bits, but if you shift, it's better to shift, by the way, the larger number than the smaller number.
Maybe that's what's happening. Maybe you're shifting the wrong number, and I just happened to get lucky and shift the right number.
You save bits that way, right? If you shift the 25 rather than the
8/3.
8/3, 2 and 2/3, you save 1 bit, maybe 2 bits. Woohoo!
I don't know. Weird.
Okay, so we can get started. And if you just came in, we're talking about an overflow bug that we saw in the Monday and Tuesday lab sections. And I actually want to just take a few minutes to talk about it because it's something to pay attention to. And it's one of those ones that doesn't throw an error. And so it's tricky. But the thing to keep in mind is, so these are the equations that we keep looking at. These are the Lorenz equations that we're integrating. And then I think it was last lecture, whichever lecture that we came up with the Euler integrator, right? We came up with this particular set of expressions for integrating those equations. And the thing to pay attention to here is the order in which you do these multiplications matters. So in the particular example of x3, right, there are a few multiplies going on here. You're multiplying x1 by x2, beta by x3, and you're multiplying both of those by dt. If you're not careful, recall that we're using 7.20 fixed point. So that gives you a range of plus minus 63. If any of your intermediate multiplies yields a value that's greater than 63 or less than minus 63, you're going to get an overflow, which doesn't break anything, but it gives you, you're integrating a different set of equations or initial conditions in that case. So you get weird output. So the recommendation is to shift before you multiply. So this is the order in which I would recommend that you do these operations. So for x1, for example, I'd suggest that you do the subtraction first, shift that, and then multiply by sigma. In the case of x2, I would shift x1 and then multiply and shift x2. And in the case of x3, I would shift x1 before you multiply by x2 and shift x3 before you multiply by beta, where these shifts are the multiplication by dt, assuming that you've chosen a power of 2 for your dt. If you do it this way, then your intermediate variables stay small enough to not overflow. Does that make sense? So I'll show you, so this is a Python simulation where I want to just show you what this looks like so that if you see this on your output, you know what it means. I'm going to define an intermediate variable called, which is beta times x3. And in the case that this is greater than 63, this is not exactly what happens in Verilog. It's not going to be set to 0, but just for purposes of showing you the general behavior, I'll say if that overflows, set it to 0. And then I'll replace beta times x3 by that intermediate variable. And when you run this, you will see this kind of behavior in model sim, where you'll get some oscillations perhaps, and then it'll go to a constant value. And like I said, this isn't an exact simulation of what happens in Verilog, so you might get slightly different behavior and more oscillations that damp out or something like this. But if you see this kind of behavior, take a look at the order in which you're doing your multiplies, because I'll bet that you have an overflow going on at some point. Okay, I'm just going to set this back so that future Hunter doesn't get confused when nothing works. Okay. The other thing I wanted to talk about before I get into stuff is Nicole and Alex have asked a question in the Monday lab. They exported their data from ModelSim. So they had their traces from ModelSim, which looked largely like these traces. And they were comparing them to the traces being generated in MATLAB. And the behavior was the two traces were exactly on top of one another for a while, and then slowly deviated, and then they were on different trajectories. And I told them, let me think about that a little bit and then get back to you. And I've thought about it a little bit, and I think I have an explanation for why this is the case, but if folks have different ideas, I'd be interested to hear them. I believe that this is a consequence, this is not any error, indicative of any error in implementation, but just a feature of the dynamics. Like we talked about, this is a chaotic system, and what that means is that the system's extremely sensitive to initial conditions. So if the initial conditions are very, very slightly off, downstream a while, you're going to be on two totally different trajectories. So I think what's happening here, I'm not sure of this, but I think what's happening is in ModelSim, in Verilog, we're using 27 bits of resolution. And MATLAB, I believe, is using some different number. Maybe it's 32, maybe it's 64, but it's some different number. So we set the two initial conditions to be the same, but over a certain amount of time, that difference in resolution is, I think, causing slight differences in the values for the state variables. And then because of the dynamics of this system, those slight differences end up on different trajectories. So if you are comparing the output of ModelSim to MATLAB and you see that kind of behavior, it is not indicative of an error, as far as I can tell. Bruce, do you agree with that?
I totally agree. It is a matter of the dynamics, and it could be something as straightforward as if beta is 8/3, which has no exact representation in binary, and you represent it by 64-bit floating point, which is what MATLAB defaults to, that is going to be a different bit pattern than the 720-bit pattern, and the least significant bits matter in a chaotic system. How far off it is will change the divergence. So if you change the 8/3 to something like 2 3/4, which has an exact binary representation, it may track for longer. But slow deviations from the MATLAB solution you expect, in fact. The way to check that is to do a 3D plot of the phase space of X, Y, and Z. And if you get the double spiral, it's working, because that is stable. Yeah, but that's absolutely right. That's the right answer.
It's the same phenomena as if perhaps in a physics class or on YouTube, you've seen the demo of people dropping a double pendulum from what looks like exactly the same location. And they track one another for maybe a cycle or two, and then they deviate. The double pendulum's another chaotic system. We're seeing that same thing just in, the simulated world as opposed to physical reality.
If you wanted to do an experiment, you could take any one of those constants, beta or rho or sigma, and change it by one least significant bit when you start the simulation and see what that does to it. I don't know the answer to that, but it would be interesting to know. It'll deviate.
Document it if you run that experiment.
Absolutely. That sounds like a discussion section for a lab report.
Okay, so what I wanted to talk about is this chart that I have shown a few times at this point. To date, we have been focusing strictly on this right-hand side of this chart. which is Verilog and then simulation of that Verilog in Model Sim. And we've been doing that because for your week 1 checkout, this is what's relevant. For week 2, this whole system is relevant. And today I want to start talking about this communication system between the ARM and the FPGA. And I'm going to do this by doing what many of you will likely do in lab, which is download a working example, open it, understand it, and then modify it and see what changes. And there are a few ways that you can communicate between the ARM and the FPGA. You can DMA from the ARM to the FPGA, use direct memory access. You can use on-chip SRAM. You can set up a FIFO. What I want to talk about today is what's probably the simplest form of communication between these two things, which is a parallel I/O port. And in introducing this and in talking about it, I will have the opportunity to introduce Qsys and memory mapping in this whole system. So that's what I'm going to do. And I want to attempt to do it in real time, which is always scary, but I have lots of people to keep an eye on me, so you can catch my mistakes. This is also, I will say, is the rest of this system, Qsys, memory mapping, it's all a bit cumbersome, and it's an example of one of those things that at least for me, when I look at any specific aspect of it, like just look at Qsys or just look at the memory mapping, it's a bit confusing, and it makes sense when you talk about they really make sense when you talk about the two of them together, because it's really something that goes together. So if, as I'm talking through this, it seems cumbersome or arbitrary or like it's not making much sense, obviously ask questions, but also hang in there a little bit until we talk about the other end. So if we're going to talk about Qsys first. When you see how it interacts with the ARM and memory mapping, it might make more sense. So anyway, that's just a caveat what I'm about to show you. So I'm going to go to the course website, and the particular example I want to look at is on the page associated with HPS to FPGA communication. And I want to look at the parallel I/O port example. So I'm going to download the whole project. And I thought too, in doing this, I can show you the process by which you open one of these projects and compile it and everything, just because, you know, it takes me 2 minutes to do that. Maybe that saves you 20 minutes or so futzing around. So we'll extract everything here. So when you've downloaded this whole zipped project, we can open this up. To open up the project within the Verilog directory, there is a .qar file, a Quartus file. If we open this, then it'll open the project. And sometimes Quartus can take 30 seconds or so to open. But there's one trick in opening this project that I want to show you, because the first time I do this, I remember spending maybe 45 minutes or so trying to figure out why this wouldn't work. And it was this. So when this opens, this window will open. Make sure your destination folder is this Verilog folder. It's not by default when you open it. And if you don't set it as this Verilog folder and you try to compile, it won't work. So just when you open this up, make sure you point it to the Verilog folder. And then we can open everything. Because we've talked so far about the Verilog that you write sort of in isolation. And I want to show you, this will show how that Verilog that you write interfaces with the rest of the system, how you tie your Verilog into the rest of the FPGA. So this too takes a few moments to open. Okay. So this is our top level module. And I want to talk through this a little bit. This is the module that you will tie your IP into. So when you open one of these projects, the first thing you see in this top level module with the name DE1 SoC computer is a ton of IO. So this is all of the IO for the FPGA. And you can see a bunch of things here. So there are a few clocks. There's the IO associated with the ADC. The IO associated with audio. We'll play with that. I'm going to talk about that in a few lectures about how to control the audio output. There's SD-RAM. There's I2C lines, a bunch of GPIO ports. The 7-segment display. This is going to be useful for you all for debugging. The LEDs are going to be useful. The PS2 ports, if you're plugging a PS2 mouse in, I suppose. Slider switches, video in. The VGA lines, we'll be interacting with those in a few lectures when we talk about writing bus masters for controlling the VGA screen. A bunch of SD-RAM, the Ethernet lines. I'd caution you against messing with these. Things might stop working. Flash, the accelerometer, GPIO, I2C, a whole bunch of stuff, right? So these are all declared, and then their input-output state and their size is also declared. And beneath all of this is where your Verilog actually lives. So in this case, beneath all of this,
I would like to make a stronger statement is don't mess with anything that starts with HPS, because that doesn't go to the FPGA side, that goes to the HPS side.
which includes the Ethernet lines, right?
Yes.
Okay, okay. So it is only in this section that this particular example actually is doing anything. And in this particular example, not a ton is being done. There's a declaration of a 16-bit wire here called hex 3, hex 0. You'll recognize these hex 4 and hex 5 wires from the IO ports up here. These are the 7-segment output displays. In this case, the 4th and 5th ones are just being set to dark. And then this is an instantiation of a module that Bruce wrote, which you'll find useful, which allows you to pass in a 4-bit binary number. In this case, it's the bottom 4 bits of this hex 3, hex 0 wire. And it will decode that into which particular segments of the 7-segment display should be lit up so that it'll be displayed on the 7-segment output. And then the only other thing that's happening is 4 wires that I'm going to talk about in some detail are being declared here. One is called PP in AXI, PP in lightweight AXI. That's for AXI bus. These are the parallel IO port lines that we're going to be manipulating. And then output parallel IO port lines. And all that's happening is at all times, we are looking at the status of switch 1. And in the case that switch 1 is low, then we set the value of PP in AXI. This in out, by the way, is input or output, where input or output is from the point of the arm. So PP in AXI is an IO port from the FPGA to the ARM, and out would be from the ARM to the FPGA. Be careful of that. It can feel backwards when you're doing this just because you're writing it in Verilog, so you feel like you're sitting in the FPGA seat. But when you're declaring these things in Qsys, as I'll show you in a moment, input output is from the ARM's perspective. So all we're doing here is, and in fact, I'm even going to simplify this because I can't control the switches from my office. So let's just set PP in AXI to out AXI plus 1, and we'll set lightweight AXI to lightweight AXI plus 1. And we'll set hex 3, hex 0 to PP and AXI. So all we're doing is looking at the value of some of these wires and assigning the value of other wires, that value plus 1. And beneath all of this is where the whole system is actually tied together. So you can see that we're tying this top level module, these wire declarations that should look familiar from above. We are tying those to these other wires whose names will become less mysterious in a moment. This is from Verilog that's generated by Qsys. So let me show you what the Qsys looks like. And if I'm going to add another one of these parallel I/O ports, and hopefully in doing that, this makes a bit more sense. So let me open the computer system Qsys module. So I mentioned a while ago what Qsys, Qsys is a graphic user interface for dragging and dropping things onto that Avalon bus and then connecting them. It provides you a visual means of doing that. So that's what we're going to see when this opens up. And for this particular example, there's not a ton of stuff on this bus, which makes it a nice one to look at. So this is what this bus looks like. There are a few things. We have the system phase lock, system PLL, which is a clock. We have the ARM on here. So the ARM side is represented on this bus. And then we have a few of these parallel I/O ports. And you can look at how some of these things are connected. So let's consider, for example, one of these parallel I/O ports. I worry this is confusing. Let's consider one of these parallel I/O ports. Let's add a new one to this bus. Maybe that's the simplest way to do it. So over here in the upper left-hand corner, there's a whole library of stuff that you can add to this bus. And some of this stuff, the manuals associated with it are trickier than others. But we can, for example, let's just add another parallel I/O port to this bus so that you can see hopefully how this works. So I've double-clicked. We can decide on the size that we want for this I/O port to be. It can be between 1 and 32 bits wide. I'm going to make this 32 bits wide. And I want to send information from the FPGA to the ARM. So that's going to be from the ARM's perspective and input. I can finish, and we see a new parallel I/O port has shown up on the bus. Nothing here is connected yet. We have to do all these connections ourselves. The first thing I like to do is rename it. So I'm going to call this my PIO. And we see we have to connect a clock line, a reset line, an Avalon memory mapped slave line, and this external connection. So we do so just by clicking whatever we want to connect this to. So the clock, we're going to connect to the system clock, like so. Our reset, we're going to connect to the system reset and to, what is this line? The ARM reset. We are going to connect. So now we have a decision to make where we want to connect this to the ARM's AXI bus. The ARM has there are two AXI buses associated with the ARM. One's the lightweight bus and one's the, I don't know what you'd call it, the ordinary AXI bus, where the difference is one of bandwidth. The lightweight bus has a smaller bandwidth than the AXI bus by an amount that I don't recall. Maybe one of you recalls what that difference is. Am I missing chats? Let me just look for a moment.
So the lightweight bus is 32 bits, and and the fixed 32, and the heavyweight bus or the normal bus is up to 128 bits wide.
Okay.
And it does all that in one cycle, so it's a lot faster for many things. I was just writing a chat that says that each bus master generates a vertical line that a bus slave can connect to. So the vertical lines all represent masters. Each vertical lane represents a driven line from someplace.
So in this case, so we can decide. So we can either hook this up to the lightweight master or the Qsys master. I'm gonna hook it up to the Qsys master. And then this final, there are different types of connections here. This last type is a conduit, which if we double click here, this will export this IO line into our Verilog so that we can manipulate this in Verilog, and then it will be communicated through these bus connections back to the ARM. And I'll show you how this works in a moment. The last thing that we need to be careful about is this memory addressing. So this is not the only slave on the Qsys master communicating with the Qsys master, and we can't have multiple slaves occupying the same memory. So if we take a look at this, these two parallel ports here are both on the Qsys master. And you can see that this parallel port goes from base address 0 to F. This one goes from 1 to 1F. We have our new PIO line currently between addresses 0 and F on in communicating with the Qsys master, which is in conflict with this one. So we can't have overlapping addresses on the for any of these masters. And these addresses here are going to be very important when we're setting up memory mapping on the ARM side. When we're mapping addresses for the HPS, we need to be very careful to match these addresses to those addresses. And we'll see all of that in a moment. So there's a lot here, right? And we're gonna revisit this a few times. And the first time that you see it, it looks like a mess, frankly. When I saw it the first time, it looks like an absolute mess. As you play with it, you'll get more comfortable with it. And we're gonna do increasingly sophisticated things with this, so hopefully it'll all become clearer. But what we've just finished doing now is adding a new PIO line to our system. And to finish this, we can click the Generate HDL button. I just want to make sure I didn't screw anything up. I think this is all fine. We can, click the Generate HDL button, and Qsys will generate a ton of Verilog for us, most of which you will never have to look at. There is one generated file that I'm going to show you that is important for you to look at so that you can tie your module to the rest of the system and eventually and ultimately back to the HPS. Most of it you'll never have to dive into if you don't want to. I mean, by all means, if you want to, you can.
The only way I could figure out how to use this interface was to start with a simple example like this and throw away a module, see what happened. Add a module, see what happens. It is like a lot of point and shoot interfaces. It's harder to describe than it is to use, but it's sort of like quantum mechanics. You never really understand it, but you do get used to it.
And by the way, it's very easy to remove things from this bus. If you decheck something over here on the left side, it will eliminate it without deleting it. So you don't necessarily have to throw away a bunch of work if you just want to turn off a module and see what happens. So in any case, what we've done now is we've generated a huge amount of Verilog, and now we can go back to our Verilog module. Hold on, my Zoom thing is blocking my icon. Okay, go back. So we want to incorporate this new PIO port back into our Verilog. And doing that is not very difficult. So what we can do here is we're going to create a new wire. Call this our new PIO port. We said that it was 32 bits wide. We can call it in Verilog anything that we want. So I'm going to call it my new PIO port. And then what do we want to assign it? Let's give it some value that will convince us that it's working. So we'll assign my new PIO port equals, ooh, I have a little parentheses error there, equals, let's say pp out axi plus 2. So on the ARM side, we're going to run this. We're going to send a value in through the PIO ports. In Verilog, we're going to read those values, add 1, or in the case of our new port, add 2, and send it back and print it out. And if everything's working correctly, we should be able to type 5 in. And when we read the values coming back through the return ports, we should see 6, 6, and 7. If things are working properly. The last step here is we need to tie this new PIO port to the Verilog that was generated by Qsys in precisely the same way as was done here. Now, the question is, what name do we put over here? What's the name that Qsys generated for this new PIO port? To figure this out, we can look at a specific file, which is in the computer system directory, synthesis directory, computer system.v. If we open this up, this is the module that was generated by Qsys, and we can scroll down and find the IO ports that we generated here. These are the ones that already existed, and here is the name of the IO port, the name generated by Qsys for our IO port. And it's the name that we specified in Qsys with export added to the end. Okay, so as far as the system is concerned, oops, I'm just going to copy this. My PIO external connection export. So if we go back in here, we connect this to, what did we call it in our Verilog? My new PIO port. And now everything's hooked up. I do want to do one more thing. I want to just make the LEDs flash so that I can demonstrate how to use the LEDs for debugging. So let's just, that won't take long, so let's just add that quickly. Let's have them flash at about 2 hertz. So if we have a 50 megahertz clock, that takes what, 26 bits. So I'm gonna overflow a 25-bit wide register. Call this counter. I want some 10-bit, we have 10 LEDs represented by a 10-bit register. So I'm gonna have some 10-bit register called LED out. And then I just want to, at every positive edge of the 50 megahertz clock, I am going to set counter equal to counter plus 1. So we're incrementing counter at 50 megahertz. And then if counter is equal to 0, which is to say it has overflowed. In that case, I'm going to increment the LED register. LED out. LED out plus. Which should just be slow enough for us to actually see what's going on. And then I want to assign the LEDs to LED out. Okay, where this LEDR, you'll remember from above all of the I/O for the whole FPGA. This is the output that goes directly to the onboard LEDs. So now if this is set up properly, we should see the LEDs counting. And I'm going to start the compilation process. We'll see if there's any problems. While this is compiling, because even though this is not tremendously complicated, this is still going to take probably 7-8 minutes to compile. I'm going to download the ARM software. We may not get through all of this today, which is fine. I'll sort of pick up where we left off. So here is the C code that's going to go on the ARM. I am going to download this. And yeah, I'll do this in Notepad.
Before going to the ARM side, could I ask a question about Qsys?
Yes, for sure.
So you were talking about like the lightweight versus the normal AXI bus. I'm just kind of curious in what scenarios will we have to use both, or in which cases can we just utilize one of the AXI buses? You know, like what's the benefit of splitting some PIO into a specific bus and then the other ones into like a lightweight bus?
So I'll answer, and then Bruce, if you want to answer this too, that'd be helpful. If you're trying to communicate stuff that's really slow, like things that humans punch into the computer, that's a nice lightweight bus kind of thing to do. Bruce, do you want to add to this?
Oh, I agree. Anything that's human-oriented input, you may as well put on the lightweight bus and use that. On the other hand, the heavyweight bus, the full bus, is what you'd use if you want to barf back a few megabytes or gigabytes of data. So it's not a strong separation, because you could say, well, even if you put the slow stuff on the heavyweight bus, humans can't type fast enough to make a difference to the data transfer anyway. So it is largely a matter of taste. There's one place that you absolutely have to use the lightweight bus, and that is if you want to have the HPS program the FPGA for you. I don't think you'll be doing that, but you could. So.
Got it. Okay, cool. Thank you.
So I want to take a look at the ARM stuff now. So this is the code that's running on the ARM. You'll recall that from the FPGA side, this whole communication with the ARM looks like Qsys. From the ARM side, it looks like memory mapping. So in the C code for the ARM, that's what we're going to be doing. And what I'm going to do is just start from the top and go to the bottom and add whatever I need to add in order to communicate with our new PIO port. So the first thing that we see here, after a bunch of includes, is these addresses for the AXI base and AXI span, lightweight base and lightweight span. These come from data sheets, as far as I understand. And many of these are, if you include, in many of the examples, there's a file called address map brl4 for Bruce.c, which includes all of these, most of the addresses that you would be using. Is that correct, Bruce?
That is correct. The AXI bus base of C0000 is hardware defined. You cannot change that. The lightweight bus base of arbitrarily FF20 is also hardware defined. The span is determined, you can change depending on how many IO ports you need, but it has to be a multiple of 4096, in other words, a multiple of X1000, because it has to be in memory pages. And the pages on this thing are 4096 bytes. So 1000 is the smallest value you can have in the span. The next one would be 2000.
Okay. And then directly underneath of this, we have pointers to the memory locations where we will write in order to communicate over these PIO ports to the FPGA. So you can see the declarations for a couple of these PIO ports already. These are those for the main AXI bus as opposed to the lightweight bus. You'll recall that we put our new PIO port on the main AXI bus. So I'm going to add another pointer here called my PIO read pointer. Okay. Very similar thing happens here for the lightweight bus. And then here are the PIO ports live at a certain offset from the base memory address for the AXI bus or the lightweight bus. And these numbers, I mentioned that we need to be very careful about agreement between Qsys and the ARM. These numbers come directly from, if we go back to the Qsys, from over here, right? So you'll recall that we had to change this to 20 to 2F because we had two things at the same memory offset. So in order to point to this particular PIO port in the C, we're going to define an offset from the AXI base of 20 in order to talk. So in order to talk to our new PIO port, so we'll say new PIO read at an offset of 20. Okay. We give a file ID, and then we do memory mapping. So we want to map virtual to real memory addresses, and we do so using this mmap function. In order to do this, the first thing that we do is open dev mem, which I suppose allows us to manipulate memory addresses. I don't frankly, No, Bruce, do you want to explain a little bit what's going on here?
Well, so as most of you probably know, Linux treats all I/O as file names, and this is kind of a weird I/O unit, which happens to be memory. So it's opening memory as if it were a file, and that's all I can tell you about it. I suspect it's so that it's syntactically correct within Linux. But then you're going to manipulate, mostly what you're going to do in the next two stanzas is to read memory addresses and virtual memory addresses and map them to physical.
Which is what's happening here. This is for the lightweight bus. This is for the main bus. We are I'll talk through these in a moment, but in effect, we're doing what Bruce just said, which is mapping some virtual memory to real memory. And in order to add our new PIO port, we need to construct something much like this, where we are going to say, what did I call it? My PIO read pointer equals unsigned int the base address plus our, what did I call it? New PIO read offset. And now when we put stuff at this address, it is mapped to a real memory address that the FPGA knows about, so that when we put stuff here, the FPGA can go to the same place and get it, and vice versa. So this allows us to take things from C, put them in a virtual memory address that is mapped to a real memory address. Qsys knows where that real memory address is because we told it when we were putting the new PIO port in the Qsys bus. Because we exported that then into Verilog, we can then do the final step of taking that value from down into the Verilog to do manipulation and then send things back. We're going to do all this again. We'll do this a few times, and as you do this, this will also become clear. But let me just finish this off. So then all that this code is actually doing is it's doing nothing complex. It's asking for a user input. It is writing that input to the two PIO ports that go from the ARM to the FPGA, and then it's reading back over the ports that come from the FPGA to the ARM. So I'm just going to add hours to this, which is my PIO read pointer. So now, okay, so I'm out of time, so I will finish this up next time because I don't want to keep folks late. I will finish by programming this device just so that you can see how to do that, because in lab, this is something that folks are going to have to start doing. So program device, I can click start. It's going to program the device. And if I open the camera here, there is at every one of your lab stations, there is a camera pointed at the FPGA. So you can see we've programmed the device and we asked the LEDs to count. You can see that the LEDs are now counting. Here, let me actually program this again and go to the camera more quickly. And oh, I blocked myself. In any case, so that's how you program, and then you can open up a webcam to take a look at the FPGA so that if you have debugging information on the LEDs or on the hex displays, you should be able to read them here. If you find that the hex displays are very hard to read, or if you find that it's difficult to tell which LEDs are lit, we can figure that out. Maybe by adding a bright light above each of these or something, we can get things to be more readable. But if that becomes an issue, then we'll take care of it. And if not, then that's okay. So start experimenting with this stuff. Experiment with it on your own. We'll revisit it together as a group. As you do it on your own, you'll generate questions, I'm sure, that we can talk about as a group. But start playing with this. Okay?
Also, let me add again, the way you start playing is take the example Hunter was talking about or some other example that has a zip file, unzip it, and program it in. There should be an existing program file. You don't even have to recompile. There should be an SOF file in the Verilog that will directly program the FPGA. Mess with it directly that way before you start beating it up.
Any other thoughts before we break for today? I'll see most of you this afternoon. Friday, folks, I'll see this afternoon. Because this is a crowded section, a crowded lab section, do your best to please show up sort of promptly on time so that we get everyone in and I can organize the breakout rooms quite quickly. With a small amount of people, it's not as big of a deal, but just with this many groups, it would help me a lot if we can sort of get everyone there at the start and then separate everyone out. Okay? Keep communicating with us. Any questions, any concerns, just let us know, okay? And we'll get things figured out. Okay, I will see most of you this afternoon.